Okay, while you're downloading,
slide. Okay, let me.
okay. So I know. Before we get to the new deck, okay. After class, yes. Last time seems like many of you came to ask me about switching, so maybe I just want to revise to go over it again. Okay. Uh, so again, there are two major switching mechanisms, right? For uh, WAN networks. One is circuit switching, right? The other one is packet switching, right? So circuit switching came first, right? Because um, in many global networks, like the global network for the LAN telephone lines, right? Circuit switching was used, right? So again, I remind you of this picture, right? Of a toy network, right? Consisting of four telephones on the left, four telephones on the right, right? So here, remember in circuit switching, okay, even though there are two switches, the major difference between the switch for circuit switching and packet switching is that for circuit switching, the switch can only forward traffic, right? They cannot store any traffic, right? So here, as I already mentioned last week, so this just a review for this. We go to the next topic as soon as possible. So here, when we have circuit switching networks, right? Uh, most of the time you have to design for the worst case, as I told you last week, right? For example, here, if in this network we assume that in the worst case, uh, all the telephones on the left could talk to all the telephones on the right? Each one on the left is picking one to talk to on the right. So, and for the sake of illustration, let's make the maximum traffic the same, right? Let's say 10 megabit, 10 megabit per second. So then in the worst case, right, you need to envision the bottleneck link to have the maximum capacity of 40 megabit per second, right? Because otherwise, um, because the switches cannot store any traffic, right? If you go over the maximum capacity in the worst case, then traffic will be lost, right? So the difference between the circuit switching and the packet switching is that now with packet switching, the switches or the routers will now have queues, right? And the reason where they have queues is because they can use the queues to store packets, right? In case uh, they need to, right? So in this case, with packet switching, okay, additional mechanism is the storing mechanism, right? The switches in the circuit switching networks, they cannot store any traffic, whereas the switches and routers for the packet switching network, they have queues and they can store packets for the case that there might be some congestion. By that I mean the incoming flow of packets to the router could be larger than the outgoing packets from the router, right? So in that case, packets will build up in the queue, right? And in this design of packet switching, okay, you don't need to always provision for the worst case, right? Because in this example, it could happen that the middle bottleneck could be, let's say, just 20 megabit per second capacity. So for the worst case, when all four on the left are talking, right, it may go over 20 megabit per second capacity a little bit for some time. In that case, the packets will build up in the queue, right, waiting for the network to become uncongested again before these store packets are being forwarded to the other end of the bottleneck link. Okay. Yes. Yes. You mean medium access control, right? So here we assume that this link is capable of fusing all the traffic. So that's why it's 40 megabit per second. That collision that you're talking about is a separate topic that we will talk about when we go over the. But you bring up a good point. It's a good assumption. But here, for this switching network, we assume that when you have a larger link, right, it can absorb all the incoming traffic without any collision, right? Okay. For example, you can do TDM or FDM, right? As long as the capacity is not beyond the capacity of the bottleneck link, we assume that everything will go through. Okay. So if circuit switching is designed to let everything to go through in the worst case. So as a consequence, in the usual case, the capacity will not be fully utilized. Okay, that's why there's a need to come up with a new type of network for packet switching to better utilize the capacity of the network. But of course, even with the queues, right? If the network becomes packet switching network becomes congested for quite a long time, there could still be packet drop, right? Because the queues all have limited sizes, right? Even though you have queue, it doesn't mean you can keep storing packets forever. In the unfortunate situation, packets could still be dropped. But for major packet switching networks like the internet, there are extra mechanism to uh, to fix this transmission loss, like retransmission through the uh, acknowledgement and feedback mechanism between the sender and the receiver. Okay, so you get a chance to learn much more about this retransmission and feedback mechanism when you learn about the TCP protocol. Okay, but it's not a topic for this course, but you get to learn much more about TCP in the other course like NetCentric. Okay, okay, that's all I want to talk about for this lecture. For as a review for the last lecture. Today, let's go over the new topic. Okay, we will not have time to finish the entire new deck. Okay, we probably need another class. Okay, but I will go. We will go roughly about half of the deck. Okay, so please get ready for the second deck. Okay, and that will be about wireless and mobile networks, right? Okay, you can see that last week lecture, right? We show like a picture of a book, right? Which is a major reference for the first lecture. That was by Forusan, right? We post the title of this major reference books for the course in the syllabus shortly. Okay, but basically there are three. There was the book by Forusan, right? There's this one that you use for many courses, including this one, right? This is about computer networks, right? The name is Computer Networking by a Top-Down Approach, right? By Kuros and Ross. Okay. In particular, this second topic will be related to chapter 7 in that reference. Okay. And it will be about wireless and mobile networks, right? Why are these networks important? Can anybody tell me? You probably take it for granted nowadays, right? Because you all have smartphones connected to a cellular network, which is wireless, right? But why do you think these are important networks compared to, let's say, the home telephone networks? What is the major benefit of having a wireless? Yeah, you can be in mobile, right? While connecting to the network. If you want to use your home telephone, you need to be at your home, right? That was why it was invented to begin with, right? And because of this, right, and the fact that the wireless and mobile networks, of course, at the beginning, the capacity cannot compare with wide networks, right? Because for wide network, the medium is uh, at a higher capacity, right? If you have a wide transmission medium, typically the capacity is much more than if you use a wireless medium to communicate. The networks are getting better and better, and now the capacity of the wireless network is good enough for most applications. So that's why you see a lot of adoption, okay, for wireless network. So this first statistics, right? Compare the ratio of mobile phone subscription to Wi phone subscription, right? And in the US, that is about 4-1. Okay. In Thailand, it's even more than that, 4 to about 30-1, right? As of 2023. Okay. Why do you think the ratio is much more in Thailand? Because many, like, maybe low income residences in Thailand, they don't even have home internet, right? They just have a smartphone, maybe with a prepaid SIM card, not even a subscription, right? Okay, so I would say the trend is that the more developing the country, the ratio should be lower, because these home Wi phones, they're still quite useful in enterprises situations, right? Like big companies, right? Another statistic is the comparison between mobile broadband connected devices to fixed broadband connected devices. Okay, so you can see that the mobile devices, the number of mobile devices are a lot more. Okay, and now, as you may know, for the cellular networks, right? They come in several generations. We are now in what generation? Huh? Currently, just look at your phone. What do you see? Your phone says in the cellular connection. What does it say? 5, right? In some area, you still see 4G, right? So yeah, for in some areas where the coverage is less, maybe you see 3G, right? So of course, 5G is better than 4G. It's better than 3G when it is available, right? But to make the connection ubiquitous, right? All of them are important, because when you go to the area where there's no 4G and 5G, it's still much better to have the 3G connection, so that you can still connect to the internet, right? Okay. So I would say the creation of this mobile networks are quite important because at the outset, right, there seem to be a lot of challenges, right? Because you have to go from wire links to wireless links. That bring up a lot of challenges that we talk about in detail. Okay. Another important challenge is think about how you connect a wireless device to the network, right? Global network like the internet, right? You need to probably go through several hops, right? The user is keeping moving, right? So how do you make sure that that user in transit is always connected to the network seamlessly? That's the issue of mobility that needs to be handled both by the wireless network and some by the end devices themselves. Okay. So in technical term, when we talk about wireless and mobile network, mobility means handling the mobile user who changes point of attachment to the network. Okay, in in a session. Okay, we discuss more about each of these topics uh, uh, soon in some in this lecture and some maybe in the next lecture. Okay, any question, comment so far? Okay. Okay, so here are the detailed topics. Okay, so today mostly we focus on the topics on the left about wireless links, network, wireless network characteristics. Okay, and for wireless networks, right? Um, what are the primary wireless networks that you're using every day? One is, of course, we just talked about, right? Cellular network. What about the other one? You can use, many of you are using it now. What about another major wireless network? Wi-Fi, right? How are they different? Cellular and Wi-Fi. What do you mean local? It's still connected to the internet, right? You mean the coverage is local? Everything is connected to the internet. Connect to Chula Wi-Fi, you still connect to the internet. If you don't have Chula Wi-Fi, you connect to the cellular network, right? Under your subscription, you still connect to the internet. So how is it different? How do you know? As long as your traffic is connected to the internet, most likely your traffic has to pass to some routers, but you just haven't seen them. Because why haven't you seen those routers? Where you see the routers for the Wi-Fi for your Wi-Fi network? You see it? That's the access point. That's not the router. Where are the routers for the Wi-Fi? That's the access point. Yeah. This is the access point. Okay. Yeah. The answer is when you have a traffic going to the internet, your traffic will have to go through certain routers for sure, right? Because your traffic is now going global and being shared with many other global traffic. So it has to pass through some routers, right? But you don't see those routers because you don't maintain them, right? So who are maintaining the routers for Chula Wi-Fi? University IT, right? What about routers for cellular networks? Who are maintaining those? Your mobile vendor, right? If you subscribe to True, for example, in its cellular infrastructure network, it has to maintain a lot of routers. Okay. Okay. For um, we explain the difference between Wi-Fi network and cellular networks. Okay, your friend brought up a good point that for the coverage availability, right? Wi-Fi seems to cover only specific areas, in particular, mostly indoor, right? You rarely see good Wi-Fi signals outdoor, whereas mobile cellular networks, they can go outdoor, right? And you can use it outdoor. Okay. So we explain the differences, going through the detail of Wi-Fi first before moving on to the cellular network. Okay. Nevertheless, both of them are wireless networks, right? And there are some common issues that both networks have to deal with, and that has to do with one of them is about mobility. We explain about mobility management in terms of principles and practice, okay, for different type of wireless networks as well. Okay, so here's the picture, toy picture of the uh, global wireless network, right? Of course, this picture is extremely simplified, right? But you see a general picture like this, where all these wireless networks, right? They all connected to the internet, right? As networks of subnetworks, right? So in this picture, how many regional networks do you see? Regional networks, wireless networks, uh, smaller networks. They are all connected, right, through this core infrastructure, right? But in terms of the smaller wireless networks, how many do you see? Right? 1, 2, 3, 4. Okay, are they all the same? Or some of them are different? Example, this one, what do you see? You see multiple, what type of wireless network is this one? Cellular, because the infrastructure device is, this is like a hub of this subnetwork, right? This picture represents what type of device? The cellular tower, right? Installed by your mobile provider, cellular provider, somewhere outdoor. You see this tall tower. You probably see some on some of our buildings here, okay, on the ceiling, right? And that's the reason why the signals can go outdoor, because it's designed to be used outdoor as well as indoor. Okay. Similar to this one, each of these smaller wireless cellular networks, right? You see a common theme, right? Which is a small area, right? Responsible by regional cell tower, right? Serving all the cellular enabled devices in the region, right? Of course, this cell tower can only reach up to a certain coverage, right? For devices that are farther away, okay, there will be the responsibility of the other cell tower. Like here, this guy cannot reach the signal from this cell tower, right? So uh, similarly for this guy cannot reach the signal for this cell tower. So this guy will have to talk to this cell tower, and it will relay the traffic of all the cellular enabled devices in this cell through this regional cell tower, right? Going to the internet. Similarly here, where here you see close by cell towers, okay, with partially overlapping regions, right? And it could happen that a mobile device moving from an area of one cell tower to another cell tower, okay? So this is the issue of mobility that we discuss in detail in the upcoming slides, okay? So logistically, these three are pretty much the same. They are all cellular subnetworks, right? What about this one? This smaller one, what do you see? Do you see any cell tower for this smaller one? No, right? So what is serving the role of the hub of this subnetwork? Instead of cellular tower, you have their access point, right? Shown here. Okay, something like this one. This one will be further connected to a router. It by itself will. This is an access point. Yeah, you see a detailed picture shortly. Okay, I think it's a misnomer to call it a router because oftentimes this guy will just connect to a dedicated router. It will not route any traffic. Everything will go to that router. Okay. Yeah. Yeah. Oftentimes the router feature is combined inside the access point, but in typical, in more complex situation, okay, I would say I would separate access point and router. Okay. Because if it's your home internet, right, it's one way will go as well. It will go to the hub belonging to the provider of your uh, Wi-Fi network, right? And then in that building, there'll be a router. Okay. Okay. So in terms of end devices, okay, the technical terms we call them hosts, right? Of course, these are all wireless networks, right? So these hosts or end devices have to be capable of connecting to suitable wireless networks, right? For cellular, what do the end devices need to connect to a cellular network? Need SIM card is for authentication, right? Basically, it will uniquely identify you to the cellular network. But in terms of doing uh, the modulation, demodulation for the wireless communication for the cellular network itself, you need the so-called cellular modem chip, right, inside your smartphones. You don't see them because they are integrated into your smartphone. Okay. Similarly, for Wi-Fi, you need the Wi-Fi chipset. Okay, in inside your smartphone. Okay. So basically, these end devices are any wireless capable devices. Okay, that are basically computers, right? So they run applications, right? If you want to be if you consider different wireless capable devices, you can see that even though some of them are connected to the network wirelessly, they could still be stationary, right? Something like a smart refrigerator, you connect it to your Wi-Fi access point, right? Wirelessly, but you don't move your refrigerator, do you? Right? So it may still be stationary. Mobile connection there is just used for convenience, right? Okay, these cell towers, okay, we call them base stations as well. Okay, they're synonyms. So because the cellular networks have to be connected to the internet, right? These cell towers or base stations, they have to be networked together, right? How is this networking done? It's the responsibility of your cellular provider, right? To connect all the cell towers, it is in charge of to the global internet, right? Basically, after the cell towers, okay, the connection will consist of both wireless links and wired links that will eventually connect everything to the core of the internet, right? So that when you use the cellular network, you can browse the web, for example, right? You can send email because all the traffic we have to go through the internet, right? So as a consequence, okay, and for the Wi-Fi network, okay, you don't have a base station or cell tower anymore, but you have the access point, right? Serving a similar role, okay. So logically, what differentiate these infrastructure devices, whether it's a base station or an access point to end devices, is the fact that the former infrastructure devices, they don't generate or consume payload data, right? They are there as relay for the traffic generated and consumed by the end devices, right? Like for example, this base station, okay, it acts as a hub, right, to relay all the traffic from all these end devices in this area further to the internet, right? In the other direction, it will be responsible for relaying the incoming traffic, right, from the internet to the destined end device, right? Similarly for this access point, okay? So all of these are wireless networks, right? So you can see that by the fact that all the links are wireless, right? All the edge links. So by that I mean the link between the infrastructure device to all end devices are wireless, right? Another important element you can see right away is that for each wireless network, right, there's a sharing going on, right? Because this for this one, for example, there's only one infrastructure device, right? But there are many possibly end devices, right? So they have to share the resource of this so infrastructure device. Okay. To that end, here the network needs to uh, deploy certain multiple access control mechanism to coordinate this sharing. Okay. And in terms of uh, communication mechanism at the lower layer, right? You see that digital communication will happen with various transmission rates, right? And many of them are based on frequency signaling techniques, right? Using different types of spectrums, right? And depending on these frequencies, okay, the signal will cover different ranges, okay? So if I have a wireless signal with lower frequency, will it travel further or nearer? When I compare two wireless signals, one with a higher frequency than the other one, which one will go further? Lower? Because yeah, that's the nature of the physics, right? Another thing is that with higher frequency, you have more chance of being obstructed by objects. Okay. Okay, this picture summarizes the two important wireless networks, right? So which ones are cellular, which one are Wi-Fi? Can you tell me? So which one are cellular? How do I differentiate between them? So remember the x-axis is the range, right? The further I go on the right, the further the signal will travel, right? The larger the coverage. What about the y-axis? Is the bandwidth, right? So the higher I go, the more maximum capacity the network will offer, right? So there are many bars, right? Which one are cellular, which one are Wi-Fi? You can see them from the names, right? Because Wi-Fi, in terms of standardization, they have the common numerical preamble to the protocol, right? That is 802.11, right? Of course, like the cellular technologies, Wi-Fi technologies, they come in many generations as well. Okay. For cellular technologies, you have what? 2G, 3G, right? Some of you just mentioned it, and then 4G, and now 5G going to 6G, right? Wi-Fi, you have versions as well. So you have B, G, N, A, C, A, X. Okay. The more recent the versions, the more bandwidth you should expect, right? Because the technologies keep getting better and better, right? At the bottom, you see another wireless network. I would say not as widely used, right? That is Bluetooth. You use Bluetooth almost every day too, but it's typically for local connection, right? Namely, the Bluetooth connected devices, they typically are not connected to the internet, right? They just, yeah. So we talk more about them in detail. Right now is AX and I believe AC, but the new one is coming. So they have nickname as well, like Wi-Fi 5, Wi-Fi 6. You know, I talk about them in detail shortly. Okay, but as you can see in this picture, here the most recent one in this picture is AX. Okay, but depending on your access point, right? If you have older access point, they may not support the more recent version, similar to your cellular network, right? When you go to some hidden areas, you may not have 4G coverage, right? Then you have to fall back to 3G. Here again, I stress the most typical mode of both cellular and Wi-Fi networks are the so-called infrastructure network, right? In which each of these sub-networks, okay, will be the responsibility of the sole infrastructure device, base station for the cellular case, or access point in the Wi-Fi case, right? Okay. In the context of mobility, when device is changing the area, okay, the network has to hand it off to a new area, right? That is when the mobile device is changing the responsible infrastructure device from one area to another area. Here that's the most typical use cases for these major wireless networks. But in some small use cases, you may see another important mode of operation as well. That is called an ad hoc mode, right? In this mode, okay, the wireless devices can communicate without any support from the sole infrastructure device. In particular, no base station, no AP. So in this case, the mobile devices transmit to other devices using the direct wireless links. Okay, but because their coverages are limited, right? Sometimes these devices may need to relay certain traffic for the other devices. Okay, you don't see this case that much, except for the very small use case of direct connection, something like Bluetooth, right? Okay, I go on for one more slide before I break. Okay, go ahead. Yeah. I just want to let you know about this, but um, we probably just deal with the column on the left. Okay, but in the study of wireless networks, okay, there are certain fancy networks, okay, that could go that the traffic could go multiple hops as well, right? So in the complete taxonomy of all wireless networks, there are 4 categories. Okay, the most typical category is the one on the top left, right? Single hop from and to infrastructure device versus the mobile devices, right? In the case of uh, ad hoc mode, okay, oftentimes it's single hop as well, but no infrastructure device. But there are certain fancy networks that the traffic could go multiple hop as well. Okay, but we will not go into them in detail. Okay, any question, comments? Okay, seems like we are at a good point for a break. Okay, let's break for maybe 10-15 minutes. Come back at around 2:20. Okay, 2:20.
Okay, so next we talk about wireless links and wireless network characteristics. Okay. So as I said, there are quite a number of challenges going from wire links to wireless links, right? Okay, one obvious challenge is the attenuation, right? Because as you can imagine, okay, if you send a signal over the air, right, it will attenuate much quicker than when you concentrate your signal through a certain type of wire medium, right? But that's not the only challenge, because for wireless situations, okay, there are many other important challenges, right? Something like interference, right? Which you can already see from your like Wi-Fi connection, right? Let's say you are in this room, okay? You are connecting to Jula Wi-Fi wirelessly, okay? What do you think will happen if you all send your Wi-Fi signal to the AP? if you don't do anything, your signal will interfere, right? So that's why you need some smart mechanism, basically medium access control, to basically allow you to efficiently share the AP's resource, right? It doesn't mean that interference could not happen for any wide situation, right? For example, you see the bus architecture already, right? Where all the tap devices are connecting to a single bus, right? In that case, there could be interference as well and has to be dealt with. But for wide situations, oftentimes interference is quite limited compared to wireless situation, and also in wide setting, it's often easier to provision to accommodate for the worst case interference. Okay. Another important characteristics of wireless links is the phenomenon we call multipath propagation. Okay. Do you know what it means? The name is already quite suggestive, right? Multipath. What do you mean by multipath? Pardon? Multi means many, right? Just imagine I'm sending to this AP, right? Over the air. Okay. How many paths you think my signal can go through? How many paths? Of course, the most obvious path is the direct link, right? We call it line of sight, right? Because remember, digital data, when I communicate to the Wi-Fi access point, my digital data is modulated into radio signals, right? Radio signal will propagate in all direction, right? In typical situation. So one major part is my signal is going direct to the access point, right? But what could be other potential parts? Remember, waves can reflect off certain surfaces, right? So for example, maybe it could go, my signal could first go down to the floor, reflecting off the floor before going up to the AP, right? Or in some angle, my signal may reflect off the ceiling or the wall, right? Of course, because these other parts will have longer distances, right? So the received signal along these other paths would be lower receive power. But again, they, in certain situation, signal going through these other parts may interfere with the signal on the main part. The reason we don't call it interference because the source is the same, right? I'm sending my signal, but my signal is going through multiple parts, but the source of the signal is still the same. When we refer to interference, it means interference from other sources. Okay. Okay, all of these will have to be dealt with in the wireless situation. That's why almost given that wireless communication is harder than wired communication, right? Important figure of merits um, to consider about wireless communication is the, what is the x-axis? SNR stand for signal to noise ratio, right? For the communication. What about the y-axis? BR stands for BR stand for bit error rate, right? So you see three lines with three colors. What do they mean? If I fix a line with one color, what kind of behavior do I see? I see this water falling behavior, right? What does it say? What did it say about the water falling behavior? It means that if my transmit power is higher, then my communication will be more effective, right? Because the communication will incur a lower error rate, right? Of course, there's a trade-off. The higher power I communicate with, the more battery I will use, right? What about the other dimension of three different colors? How are these three colors different? So one figure of merit is the signal to noise ratio. The other figure of merit is bit error rate. What do the color represent? What are the legends for different color? Going from the bottom, BPSK. Have you heard of BPSK? What do you think it stands for? Binary phase shift keying, right? QAM 16, what do you think stand for the 16? QAM 256. By the way, did you take digital communication already? Introduction to digital communication. Digital communication, did you take it? Okay, what do you think BPSK, how do you think BPSK is different from QAM 16, QAM 256? What do you think is the difference? For 16 to 56, what can you observe from the numbers? 16 is 2 to the 4, right? 2 to the 4. 256 is 2 to the 8, right? Pardon? Binary, yeah. So at the bottom is binary phase shift keying. So let me tell you, maybe you haven't heard of it. Okay, these are different modulation schemes. Okay, the higher the modulation, the more bits you pack into the communication symbol. In particular, BPSK, you pack only one bit. Okay, one communication symbol will be decoded as 0 or 1, right? Whereas for QAM 16, as the name suggests, there are 16 possibilities for one communication symbol encoding 4 bits, right? Because 2 to the 4 is 16. So when you communicate with one communication symbol, you communicate 4 bits simultaneously, okay? Similar to 256, one symbol contains 8 bits, right? Of course, the more bits you pack into one symbol, right, the more confused the receiver will become, right? Because for BPSK, the receiver has to differentiate only between 0 and 1. But for QAM 16, for example, the receiver has to differentiate between 16 possibilities, right? So the higher modulation you go, okay, going from blue to red to green, right? If you fix the signal to noise ratio across all these three modulation schemes, the higher modulation you go, the higher rate of transmission you will use, right? But at the same time, it also incur larger error rate, right? So there's a trade-off going on between rates and error rate, right? So of course, you're sending more information with 256, right, than 16 and subsequently BPSK, right? But the higher rate you communicate, the higher error rate, the communication will incur as well. Okay. And one thing that you always have to consider is because in wireless network is because the end devices, right? They can move around, right? When they move around, okay, they will encounter different signal to noise ratio depending on their locations, right? And that will have the implication to the error rate and the maximum rate that can be supported by the wireless networks or wireless links, right? So when we talk about wireless link, typically is one sender, one receiver, right? But the situations get more complex quite rapidly when we consider wireless network with more than uh, two communicators. So in this case, there are three communicators A, B, C. Okay. This network situation will create additional challenge. Okay. One primary challenge is the situation we call the hidden terminal problem. What do you think it means? Hidden terminal problem. Who is hiding from who? Pardon? So which one is hidden from which one? Hidden because, so there are three uh, devices here, right? Which one is hidden from which one in this picture? You said C is hidden from. Why is C hidden from B? Only A and C are hidden for each other, right? Because there's an obstruction going on. So neither C can hear A signal or vice versa, right? But in terms of B and C, as well as B and A, everything is fine, right? So in this case, because of this obstruction, okay, A and C, they cannot hear each other. So that means if they happen to communicate simultaneously, they would not have known of their interference at B, right? And that could cause problems in the network situation. The picture on the right show another scenario where logically the same situation can happen, but the cause here is different. There's no obstructor going on. Here, the fact that A and C are hidden to each other happens because they are further away, right? So here, because of the attenuation, right? And because of the nature of the receiver and the transmitter, there is a typical threshold on which the signal have to go beyond for the communicators to understand each other. So here, if A and C are further apart, right, it means they will not hear each other, even though there's no obstructor. Okay. So that's why you can see that in wireless networks, right, it's important, okay, to have a mechanism, okay, to control access to the wireless network resource, right? This could be wireless resource that are shared across all mobile device to the access point or to the cell tower, right? So an effective medium access control mechanism widely used in wireless network is a scheme called Code Division Multiple Access, CDMA. Have you heard of it? CDMA. What do you think it does? as the name suggests. So here, the way different devices are sharing the wireless resource is controlled by unique codes assigned to different users. Okay. These codes act as a certain partitioning mechanism of the entire resource to different users. Okay, you see it in clearer in the picture. Yeah. So it's not the resource is not separated in either time or frequency explicitly, but everyone will share all the time resource and frequency resource, except that you partition the signals according to predefined, well-selected codes. Okay. And the picture would be something like this. Okay. So here, okay, let's just show it for one user first. Okay. So in this situation with CDMA, okay, for the fictitious scenario with just one sender and receiver, okay, let's say sender has some bits to transmit, right? Particular could be this could be for bit one. When you modulate it to -1, could be for bit 0, right? So in CDMA, the sender will not send this directly to the channel, but rather it will modulate it with the code first. What's the code? This is the code. So you see this bit interval is further split into sub intervals. Okay. And as you can see, in each bit interval, the signal is further multiplied with this code sequence. Okay. Different sub intervals are called chips. Okay. This entire sequence of 8 chips is called the shipping sequence, right? You can see this shipping sequence is fixed for a particular user. And when you have bit 1, okay, of course, if you multiply it with this shipping sequence, you get the same sequence. But when you have -1, you're just flipping the sign, right? This shipping sequence is carefully selected for the different users, and it will be known to the network. So if there's a receiver who wants to receive from the sender, it will have to know the shipping sequence for that sender as well. And the way we do decoding is by doing the inner product, okay, of the received signal, right, which is also created by multiplexing the data bits with the chip sequences. Okay. So receiver will do the inner product of the received signal with the same shipping sequence before doing this thresholding. And you can see in this picture, because of the sign flip, right? When you do this inner product, you get the original signal back. Okay. This is not hard to see at all. Okay. For any shipping sequences, it will work, right? Because I'm sending 1 or -1. And if I multiply any shipping sequence to itself, I basically get 8, right? Divided by 8, I get 1. But if I flip it, right, then I get -8 divided by 8, I get 1. But these shipping sequences are designed to be useful for the case where multiple senders are sending together simultaneously. So here you have 2 senders, okay? Sender 1 and sender 2. The shipping sequence for sender 1 is the same as I show previously, right? What's different here is the shipping sequence for the other sender. Okay. The mechanism for communication for each sender is still the same. You multiply the payload signal with the corresponding shipping sequence before you sending them. And if you send them simultaneously, they get added over the air, right? So that's the combined receive signal consisting of both information from both senders, right? But of course, at the receiver, it wants to separate out the signal for the different users, right? So how does it do it? So the magic happens here because even though there is interference, the receiver can still execute the same decoding mechanism by doing the multiplication of the received signal with the shipping sequence of the target sender, right? Let's say this decoder wants to decode the signal from sender 1. It will first multiply the received signal with this shipping sequence belonging to the sender 1 before performing the inner product and thresholding. And in this picture, you can see by calculation that it does get back the signal of the first sender. So what if this receiver wants the signal from the second sender? What does it do? What does it have to change? Change the code, right? Because this code here is for sender 1. If it wants the code for sender 2, which code will it has to use? It will use this one instead, right? And you can verify by simple calculation that you will also get back 1, 1, which were the original bits sent by encoded by the second sender. Of course, our natural question is, can any codes work, right? Do you think any codes, any pair of codes I choose for sender 1 and 2 would work like this? Remember, this has to work all the time. If the multiple access control mechanism here is to work, right? Because here I'm just illustrating for this particular 2-bit sequences, right? But if it is a good mechanism here for the medium access control, this has to work for all data bits for sender 1 and sender 2, right? So my question is, does this always work no matter what pair of codes or shipping sequences I pick for both senders? Okay, I would urge you to try this out, right? Pick a random shipping sequence for 1, pick a random shipping sequence for second, maybe reproduce this example to see if you get back the original sending data bits. Okay. If so, explain why any codes would work. If not, what are the special property of the code that will make it work? What do you think? What do you think is correct? Any pair of codes would work, or I have to pick special pair of codes? Which one do you think is correct? Sorry? Special, how special? Special is correct, okay? You can simply see why you have to, why any pair of code would not work, right? Because what if I pick the codes to be the same, right? Then I cannot differentiate anything. But so I have to pick them judiciously. But what are the property of these codes that I have to use? What do you think? We do like sending, encoding, decoding by what type of process? We doing multiplication and then sum, right? That's basically the inner product, right? So when I do inner product, it's like I'm projecting the signal in 2 degrees of freedom, right? So if I want the degree of freedom of the two user to be orthogonal, what do you have to pick for the shipping sequences? The answer is their inner product should be 0. That tantamount to orthogonality in linear algebra. Okay. And how do you verify that? For this example, what is the shipping sequence for the first sender? 1, 1, 1, minus 1, 1, minus 1, minus 1, right? Minus 1. What is the shipping sequence for the second sender? Is 1, minus 1, 1, 1, 1, minus 1, 1, 1. What is their inner product? Okay, I can do it one by one. 1, 1 is 1. 1 minus 1 is minus 1. So the first two cancel, right? 1, 1 is 1 again. Minus 1, 1 is minus 1. So it's cancel again. So I'm done with the first 4 ships, right? So now the second 4 ships, 1, 1 is 1. Minus 1, minus 1 is 1. So it becomes 2, right? Then the last two are minus 1, and 1. That's minus 2. So overall, the two codes are orthogonal, right? Because the final 2 will cancel with the final minus 2, right? So what's amazing is I can pick any coding sequences I like as long as they are orthogonal. Okay. As you can see, even though this works for 2 users, right? You can imagine the situation will be more complicated with more users, right? Because you need more codes. All of them has to be orthogonal to one another. Okay. Or if you go for more and more users, this may not be possible, right? Okay. Any question, comments? Okay, now we have only an hour left, so I go a bit faster to talk about Wi-Fi, right? So this was asked earlier about what we are currently using, right? You can see it in this picture, okay? The more recent of the generation for the Wi-Fi standards, the lower you would go, right? As you can see, the years of ratification, right? The newer generations will give you more data rates and potentially higher range. The ranges wouldn't change much because that depends on the spectrums under use, right? But these spectrums change at a much rarer occasions. As you can see at the beginning, only one spectrum is used, 2.4 gigahertz. And then when the bandwidth requirement become increasing, okay, another band is at 5 megahertz. And now the third band is being added to provide more bandwidth as well, okay? But, okay, the higher you go for the frequency, the lower coverage you will get, right? So what set the range is basically the lowest frequency, which cannot be added any further. Okay. So again, for Wi-Fi, the infrastructure device is the base station, the access point, right? We call it base station as well to conform with the cellular network. Okay. But for Wi-Fi, we know that it's the access point, right? So you can see in the typical configuration, right? The small Wi-Fi area are organized into the so-called basic service sets, right? Each consisting of only one AP. They will all connected to the internet through the so-called gateway router, right? Okay, again, all the devices in the basic service set share the single access point, right? So the spectrum to and from this share access point has to be divided, right, into different channels according to the frequency. Okay. Basically managed by the AP admin. Okay. Of course, there's only limited number of channels, right? Because the spectrum is limited. Okay. Regardless of how efficient you do this partitioning, right? Interference can still be possible when multiple users are assigned to the same channels. Okay. So basically, when you want to use a Wi-Fi service, right? When you first go into a new Wi-Fi network, right? You have to do the association, right? To allow you to connect, right? So one obvious way where you can see this, if you go to a new Wi-Fi network, right? Which you have not put in the password, you need to first put in the password, right? That is happening after the process of association. And this process of association involves the mobile device scanning for the available channels and listening to the so-called beacon frames to allow it to know the AP a little better. By that, I mean knowing the AP SSID and MAC address. Okay. Then after that, the device, okay, can pick an appropriate AP to associate with, followed by authentication, as I already mentioned, before the protocol called DSCP is being run to get the IP address in the AP subnet, right? So the scanning that I mentioned can happen both passively or actively. Passive meaning the mobile device is passively listening for the beacon frame sent by APs, whereas active means it initiate the request for these beacon frames. Okay. So to mitigate the interference, okay, Wi-Fi has a mechanism to avoid collisions by multiple mobile devices. This mechanism is called carrier sense multiple access. Okay. So as the name suggests, here the Wi-Fi devices try to sense the medium for its availability before attempting any transmission. Okay. Because if the channel is not available, okay, meaning occupied by the other user, and the Wi-Fi device try to attempt the transmission, it may interfere with the existing signal, right? If you know the code a little bit, you may know that parallel technology to Wi-Fi is the LAN technology, right? That also comes with the preamble 802.11, and partly because that Y technology 802.11 for Y cable. Okay, it's also used CSMA as well, but there additionally it uses the mechanism called collision detection. Okay, try to retract the communication when collision is detected. But here for Wi-Fi, because that collision will be hard to detect it, Wi-Fi instead adopts for collision avoidance. Okay, and I will explain in detail what this means. Okay, so this collision avoidance goes like this. Okay, first, before any Wi-Fi sender will attempt the transmission, it will first sense the wireless medium, okay, to see if it's idle or not, meaning there's no other pending communication from other device, okay. It will sense the channel for a suitable predefined period of time called DIFS, okay. If the channel is available for that interval, okay, so if the channel happens to become busy during that interval, okay, the sender will not attempt any further communication of the real payload, but rather it will back off, right? Meaning wait for the future before attempting the real transmission. And the way this done is by using the back off time, right? To back off before attempting the new transmission, okay? This done by setting up a random back off timer that counts down, okay, for the predefined period of time, okay, for the channel to remain idle before attempt the new transmission. So in this picture, if the channel is not busy for this period of time, then the sender can continue sending the real payload on the, okay, after the reception of the sending data, okay, it will also wait for another predefined period of time, okay, before returning the acknowledgement frame, okay. And the reason why this acknowledgement frame is needed, because in wireless situation, there could be the hidden terminal problem, right? In addition to that, okay, the Wi-Fi devices, to mitigate the collision, they also use the mechanism called request to send and clear to send, right? So in particular, the sender will first transmit a small request to send packet to the base station, okay? And as the name suggests, this is not the real transmission, but rather is an acknowledgement to the base station that, okay, I want to send. Are you clear to receive my information or not, right? So in that context, the base station will respond to a suitable clear to send to just one sender, after which that sender will commence with the real communication. So the way it works is something like this, right? Let's say you have two terminals, okay? They may attempt to transmit at the same time, but due to this mechanism, before they can send real data, they have to negotiate with the AP first, right? That is done to the request to send frames, okay? If they happen to send the request to send frames at the same time, the frames may collide at the AP. In that case, the AP will not allow neither of them to transmit, right? But wait for another time. Remember, this request to send frame are sent according to this back off mechanism that we already mentioned, right? So if there's a collision, okay, both will back off, and for the new opportunity to send, it could happen that only one sender is trying to send, right? So in that case, it will user A will send the request to send frame again. If it accepts successfully at the access point, the access point will broadcast clear to send to all the devices in the network, right? In the subnetwork. So oftentimes this clear to send frames will be heard by everyone, okay? And then sender B will know, right? Because this clear to send frame has the user identity associated with it. User B will know that, okay, after this reception, it should defer the transmission, right? Allowing user A to send the real payload to the AP. After successful reception of the real payload, the AP can acknowledge the successful sender with its identity included in the acknowledgement frame. Okay. Here's a little more detail of Wi-Fi frame. Okay. The numbers here represent the bytes, right? There are many fields, but I would argue most important fields are these 4 addresses. Okay. We will use 3 in the infrastructure network infrastructure mode. Of course, a frame is sent from a transmitter to the receiver, right? So there must be the MAC address of the transmitter and the MAC address of the receiver in the first and the second field. But in Wi-Fi, it also uses the third address here, which is the MAC address of the router interface attached to the AP. And the reason is, as I already mentioned, each AP will be attached to a gateway router, okay? That will further forward any packets from this Wi-Fi subnetwork to the internet. So that's why this third address is used in this second hop from the AP to the gateway router. So the picture will look like this. If you look at the frame starting from host 1, right? Of course, the transmitter address will belong to the AP. The receiver address will belong to the the transmitter address is in the second field here, belong to the host. The receiver address belong to the AP, but it's also put in this third address of the gateway router attached to this sole AP, right? And the reason this is used because after the first hop, this frame will need to be encapsulated to be forwarded to this wire link connecting the AP to the gateway router, right? And that has the transmitter address being the MAC address of the host, and the destination address being the MAC address of this gateway router, okay? Before it can be further forwarded to the internet. Here's a more detailed dissection of different frames, right? We learn about the 4 addresses. Last one is used only in the ad hoc mode, okay? This one is a payload. Okay. Frame control for 2 bytes are further splitted into these subfields. Okay. Including protocol version, type, subtype, bit showing whether this frame is to AP or from AP. Okay. And other control bits. The second important field is the duration of reserved transmission time for request to send and clear to send. The payload data is put into this field. Okay. Sequence, frame sequence is there for the acknowledgement scheme, right? To allow for reliable transmission. In case some frames are lost, those frames can be retransmitted. Okay, of course, we're talking about Wi-Fi network as a type of wireless network, right? So mobility can happen, okay? So we first consider a very mild situation where a host on end device moving from one Wi-Fi cell to the other nearby Wi-Fi cell, right? So in this case, if this mobility will remain in the same IP subnet, then the IP address can remain the same, given the fact that this switch can know from which port the traffic of the mobile device coming from. So originally, if it's in this region, right, the traffic of H1 will come from this port. When it moved to the other region, the switch can self-learn to remember that, okay, after the movement, the traffic of H1 will come from the alternative incoming port instead. Okay. Additional capabilities of Wi-Fi protocol, okay, related to this waterfalling curves that we discussed, remember, about the trade-off between the error rate and the maximum transmission rates, right? Is the capability of allowing the base stations or APs to dynamically change the transmission rates depending on the situation, right? Because if it so happens that the mobile move further away from the AP, then the SNR for the communication will be lower, right? So in that case, the base station can change to go for a lower modulation scheme to allow for better bit error rate, right? So for example, if originally the host is very close to the AP, it may go for the highest modulation scheme first, right? When the Wi-Fi device starts moving away, so basically you're moving to the left of the x-axis, right? Then the BER will increase, okay? Once the BER become intolerable, right? Then the base station can switch the modulation down, moving to a lower modulation, in this case, going from green to red to reduce the bit error rate. But at the same time, the supported rate would be lower as well, right? Because you use a lower modulation scheme. Okay, another additional important capability is there for the Wi-Fi devices to save some battery, right? This related to power management. Okay. So basically, this is a mechanism that will allow devices to go to sleep whenever they can, right? So for example, this allows for the node to communicate to the access point that the node is going to sleep until the next beacon frame, so that the AP would know that the mobile device is sleeping and not to send it any traffic during the sleep. In addition to node to AP signaling for power management, the beacon frame from AP to the mobile devices also contains suitable information to allow for this power management. In particular, the beacon frames can contain a list of mobiles, okay, with pending traffic destined to them, right? So then, okay, once the mobile devices hear these beacon frames, if they can see in the beacon frame that there are some pending traffic destined to them, then they will not go to sleep. But if they don't see this, then they can go to sleep until the next beacon frames, right? Okay. Any question, comments about this? Yes. Beacon frame are from AP, broadcast from AP to everyone. So basically the idea is that it's called beacons, right? It's like beacons in real life. When you heard about beacons, it's like a broadcast signal for everyone that heard that hear the beacons to perform some action. So here, because before any communication can happen, the mobile device will have to associate with a suitable AP, right? So that's why these beacon frames are there for all the devices that can hear to decide whether it wants to associate with the AP or not, right? Beacon frame are for mobile devices, but it broadcasts by the access point, right? So here you can see the picture here. So here, let's talk about passive, right? Passive scanning of the mobile devices of beacon frame. So here, consider two nearby APs, right? They can both broadcast the beacon frames with number ones here, right? So if this mobile device is further on the left, right, it can possibly hear only the beacon frame from here, right? So in that case, it's easy, okay? If there's only one beacon frame that it hears, it will associate it to the AP broadcasting that beacon frame. But in this rarer situation where it hear both, right, then it can decide which one it will associate. So in this case, it decide to associate with the second AP instead, okay? Continuing with step 2 and 3, okay? That's the major mechanism for beacon frames to do the association. But here, we saying that additionally, if you put more information, more information in the beacon frames, this information can be used for effective power management as well, okay? Because in the direction beacon frame from AP to everyone, right? So in this direction, okay, apart from the beacon information itself, it can contain extra information about mobile devices for which there's some pending traffic, okay? So once this mobile device here, this beacon frame, it can see whether there's a pending traffic to it or not. Right? If there's a pending traffic, then it should not go to sleep, right? Because after the beacon frame, there may be the payload coming to it. But if it's not in the list, then it's free to sleep until the next beacon frame. Okay. The mobile devices, yeah. The host, yeah. The AP will never go to sleep because AP is more power efficient, right? When I talk about so like here, oftentimes the AP is powered by a wide connection. Okay. For power management, mostly it's for Wi-Fi clients, okay, or mobile devices. Okay. Before we close for today, I just mentioned briefly another type of Wi-Fi network, okay, that is mostly used locally. Many of you know it, Bluetooth, right? Like this headphone of mine is connected to my laptop using Bluetooth, right? But my headphone is not connecting to the internet, right? So that's why for this Bluetooth network, oftentimes the range is much shorter, merely just to use to replace the cable for convenience. Okay. And because it's a much shorter range, you don't need a special infrastructure device. Okay. The spectrum's use is at the low frequency, but the bit rate is also low. Okay. The way this Bluetooth network works is that the devices are organized into master and clients, where the master will poll the clients and grant requests for client transmission. It will also have a power management mechanism as well. These devices that are going to sleep are called PARP device or inactive devices. Okay. In terms of medium access control, it uses both time division multiple access control and frequency division multiple access control with multiple frequencies. Okay. I already talked about PARP mode for power management. It also support a certain bootstrapping mechanism to allow the Bluetooth nodes to self-assemble into a small sub-network called Piconet. Okay, that concludes our discussion. As you can see, we went for about half of the deck, right? We will not have time to finish the entire deck. So next week, we switch gear from Wi-Fi to cellular, okay? But at the beginning of the class, prepare to do some quiz on Wi-Fi and Bluetooth.